Welcome back. The next case study from Bosch Bangalore is on productivity improvement in gear shaft through machine learning technique. In this case study, Bosch will address the gear grinding process establishment in a 2-decade-old conventional grinding machine, 3-stage to single stage, aided by machine learning driven tooling cost reduction, leading to doubling sales with reduced resources. To know more, I now invite Mr. Prabhakaran and Mr. John Victor from Bosch to take us through their journey and share their experience with us.
On behalf of Bosch Limited Bidadi plant, I welcome one and all present here. We at Bosch Limited, we are manufacturing high pressure fuel injection pumps to our esteemed customers. Few of the customers are listed here. Our project is productivity improvement in gear shaft through machine learning techniques. Our team members are Mr. Chandramohan, heading methods function. I am Prabhakaran from methods function, and Mr. John Victor from quality function, and Mr. Ravi Shankar from manufacturing. This is the market analysis done by Allied Market Research Team for hydraulic gear pumps. Analysis shows that the gear pump market is growing to the extent of 10.4 USD by 2022. And as you know, Bosch is the leading manufacturer of hydraulic gear pumps across the world. On the other end, the market is having huge competition and also competitors. This pie chart explains how the total volume of production of hydraulic gear pumps, and Bosch India team is contributing 9% of the volume to the total worldwide. Due to this increased volume, there is a gap between the manufacturing and supply. And this talk time chart shows that OD grinding process is the bottleneck for the entire plant. And also, this water flow chart shows how Bosch Bidadi team and Bosch Hejala plant, that is the Rexall team, have collaborated and improved their productivity over the time. In 2019, we supported them by process optimization and improved their plant capacity by 300 numbers. Similarly, in 2020, we improved their plant capacity by 400 numbers. And this year, in 2021, we improved the plant capacity by 900 numbers. And how we went about this massive productivity improvement will be explained in the further slides. As I told, to fulfill this gap, the Bosch Rexall team needs to invest more than 80 million rupees. Since the ROI is greater than 5 years, they approached Bidadi team for productivity improvement. We taken as a challenging task to improve their productivity by more than 30% during this pandemic situation. Also, for us, Bidadi plant, it is an additional revenue of 50 million INR by utilizing our old excess MAEs. By this way, it's a win-win situation for both Bidadi plant and also Hejala plant. This is our vision statement of Bidadi plant, and this project comes under lean processes and excellence in operations. In a nutshell, the project is taken in 3 stages. The stage 1 is establishing the gear shaft grinding processes in our conventional machines and reducing the cycle time from 152 seconds to 75 seconds. The stage 2, the gear thickness reduction through shine-in approach, and the stage 3 is using machine learning techniques, reducing the tool cost. We have approached DMAC approach for this gear shaft establishment process. Let us understand how the manufacturing process carried out in Hejala plant. This is the explorer view of the gear pump, and in Hejala plant, they are doing the OD grinding in 3 stages in a conventional machine, and each stage they are consuming 50 second cycle time. And some of the quality requirements are the diameter tolerance are ranging from 5 micron to 12 micron, and the dimensional and form tolerance are requirements from 2.5 micron to 6 micron. The total cycle time is 150 seconds, and this product calls for a closed loop grinding for OD and the thickness. Initially, we approached the OEM to establish this OD grinding process in our XSMAE, that is a Juncker machine. That machine having 2 spindles. The advantages of this machine is this is a high-speed machine and also having auto unloading feature. Considering the huge modification and the time and cost involvement, OEM rejected this proposal. And then second proposal is we formed an internal competency team and tried to establish this process with Bosch competency only. And the first and foremost challenge is to achieve the concave surfaces on the gear flange. On the controversy, we have only straight plunge grinders. The straight plunge grinders are nothing but the work head axis and the wheel head axis are perpendicular. This will lead to a convex surfaces or a straight surface on the gear flange, that is 0 to 2 micron. This is not acceptable. So we have gone for tilting this wheel head by 1 degree so that the wheel head axis and the work head axis are in the 1 degree angle, so that the concave profile we could able to achieve. For that, we have modified more than 30 NC program to achieve this concave profile. The next challenge is the conversion of OD grinding gauges to thickness gauge. On that machine, we have 2 gauges on the machine. Now we need to convert this OD grinding gauges to the thickness gauge. For that, we have design and manufacture this mounting block, and then many PLC modifications are done and accommodate this thickness gauges. We have avoided the additional investment of 0.8 million INR rupees. The next challenge is this converting the centers to the friction drive centers. We have eliminated this jaws and used the center as a driver. For that, we introduced this friction centers. We have collaborated with many experts across the Bosch to develop this tooling technology. Also, we have developed grippers, fixtures, and trays, and modified many plot programs to establish this product in our conventional machine. The next stage is integration, process integration. For that, this machine have a 2 spindle. The first spindle is used to grind the journal diameter 1 and the gear OD 1. The second spindle is used to grind the journal diameter 2. By this way, the 3-stage process will be converted into single-stage process. Let us understand from this video. This is the spindle 1 and spindle 2, and spindle 1 is grinding the journal diameter 1. Now the spindle 1 is grinding the gear diameter 1. Now thickness gauge is measuring the thickness. Now the spindle 2 is grinding the journal diameter 2. By this way, we could successfully establish this 3-stage process into single-stage processes. The next, after establishment, we have analyzed our results in terms of quality, cost, and delivery. Coming to the quality, we could able to successfully achieve all the quality parameter except the gear thickness. Since the CP/CPK is less than 1 and this leading to rejection, quality targets are not achieved. Coming to the cost, since the defect cost is more and also tool cost is high, the cost target also not achieved. Coming to the delivery, since the cycle time is 72 seconds, we could able to meet the customer requirements, but not the quality and cost. What next? There are only two options. Only we need to improve the process or drop the project. Now our team has gone for two innovative ideas to improve the process. The first idea is gear thickness variation reduction through shine-in approach, and the second idea is adaptive dynamic dressing to reduce the tool cost through machine learning techniques. Now the next further slides will be explained by my colleague Mr. John Victor.
Welcome you all. Myself, John, representing from the quality department. I'm going to explain the second stage of our project. That is the gear shaft thickness variation reduction project through the innovative tool, which is called a shine-in approach. First, let us understand what is meant by shine-in. Shine-in is an advanced quality tool which is being developed and used across the many industries. The main advantage of shine-in is used to solve the problem by using the complete data approach, data-driven tool, and also it is a user-friendly tool. The main difference between the shine-in and the Six Sigma tool, it is in Six Sigma we have used the 5-step approach, that is a DMAC. Whereas in the Shine-in, we have used the 7-step approach. The 7-step approach is nothing but focus, approach, converge, test, understand, apply, and leverage. Yeah, I would like to explain from the first step. The first step, it is the focus. Here we'll be focusing on the problem. The problem is nothing but to reduce the internal defect cost, to reduce the gear shaft grinding process. This particular gear shaft thickness variation was contributing around 0.62 million INR. And the second step of our project, it is approach phase. In the approach phase, we will be defining the problem in more detailed way. That means that it is very evident that in the graph, the thickness variation was contributing around 10.1% of our total rejections. So our technical problem here, it is gear shaft thickness not meeting the specification of 5 microns. And here we have attached the process capability study, and we could able to identify the best of best samples from the green highlighted curve area, and also we have selected the worst of worst samples from the blue zone area. Next stage, it is on the converge stage. This is the very important stage for the problem solving, which is called a feature strategy diagram. In this particular stage, we will be analyzing the contrast relationship of the each and every parameters. For example, we have analyzed the gear point 1 to point 2, and also we have analyzed the existing gauge line 1 and line 2 point, and also we have analyzed the gear plane 1 and plane 2 point, and finally we have analyzed more in detail by using the QStat software analysis. We have analyzed the complete process behavior trend, and it is very evident that there are many parts which is not within the specification, which was leading to the high rejections. Next part of the feature strategy diagram, we have also analyzed the type to type, machine to machine, plant to plant, and also time to time. This will be explained very in detail in the next slide. We have done the multivariate analysis tool. This is a very special statistical tool which helps to analyze the relationship of the multiple parameters. For example, in this case, you can be very clearly evident that the supplier wise we have analyzed, type wise, and also part wise. In this particular case, the supplier wise, the supplier 1 and supplier part number 1 and 2, there is no variation, it is constant. Whereas in the supplier 2, in the type number 2, there is a high contrast. This was confirming that type to type and within the type, supplier to supplier having high contrast of variations. Next step of a problem solving, it is the converge stage. This is a very important stage for the solution development. This particular stage, we have analyzed the problem thickness variation in more detailed way. For example, we have analyzed the measurement part and also the process part. We have used this tool called isoplot chart. In this particular tool, it helps us to arrive the discrimination ratio around 13.5. That means it's nothing but when the measurement error, it is 13 times, it is less than the process. So that we are eliminated the measurement part and we are focused on the process part here. In the process part, the high contribution for the variation, it is input material and the grinding process. In the input materials, we have measured all the parameters, it was found okay. And then we are focused on the grinding process. Now let us understand the importance of the grinding process here. Let us understand the advanced grinding process which is developed by our German engineers. Before actual grinding process starts, the part is flagged outside the machine and center to collar is captured using the LVDT probe. Flagging is the process to capturing the relative distance of the workpiece collar with respect to the between centers. This value is fed into the machine CNC and accordingly the Z-axis position adjusted. Now the spindle 1 starts grinding workpiece side 1. Then the thickness gauge is forwarded and the total thickness is captured through the T1 and T2 probe as it has been clearly identified in the diagram. Now the spindles 2 starts the grinding workpiece side 2 while the thickness gauge is in the forwarded condition. Once the thickness value has been achieved, the gauge thickness gives a signal to the CNC and then the cycle ends. All these complete cycles which I was shown in the slide, it has been happening in the real-time basis. Okay, next we have done the validation of the flagging position inside and outside the machine, and as per the analysis, you can able to clearly evident that the trend chart was clearly giving a message that is not having a much variation. So we have ruled out this particular process since the values are consistent between machine and the flagging centers. Next, we have done the study called regression analysis tool study between the T1 value and the gear shaft thickness value. This is very important step to arrive the root cause because this particular regression analysis tool helps us to identify the correlation between T1 value and gear shaft thickness. Here, the R square value was around 72.8. So there is a strong correlation between T1 and gear thickness. Okay, now the red X aspect is on the thickness gauge of T1 and T2 mounting existing gauge design. So out of 4 variables, the high contribution on the T1 and T2. Now I would like to explain what is the influence of the T1 and T2 value during the workpiece grinding. When the flagging position is at 0 position, then the T1 and T2 value will be symmetric. There is no influence. Whereas when the flagging position in the positive direction, you can see the T1 value was quite high, so that the gear thickness results also will be in positive. Similarly, when the flagging position is in the negative direction, then the gear thickness results will be negative due to the very less T1 value. Higher the pre-part variation, higher the T1 error. Next, and also we have approached the measurement gauge specialist, which is Janoptic in Germany, and they have a proposed one solution, that is to measure the T1 and the T2 values separately by using this special gauge. But whereas this particular proposal is having a one disadvantage, it is nothing but it is cost. The cost was contributing around 1.1 million INR per gauge. And also due to the space constraint, the team have identified that this particular solution is not practically feasible, so we have dropped this idea. Next, along with our team, we have done the brainstorming session. Along with our software analysis, we have done the complete process chain analysis supplier wise. And here we could able to see the histogram. Each supplier is behaving differently. For example, the supplier A, which is indicated in blue, another supplier in B, another supplier C. The process variation is quite different because the range of each supplier is quite different. And it is very evident that considering the trend in the pre-parts, we have introduced the identification on the supplier and batch wise to analyze process further. And also we have machined the parts as per based on the identification. And this particular supplier-wise identification process concept, we have validated with the 5-penny test. By 5 batches have been tested with the mixed part conditions, and also we have machined the 5 batch tested parts with the segregation as per the supplier identification. And this particular diagram, it is very clear that the sigma value of before, when we are supplying the mixed condition, the sigma value was high, whereas the supplier-wise identification batch, the sigma value was drastically reduced. And this was confirming that the quality level is improved, and also we could able to achieve the required quality with the very low rejections. Next, as a final part, we have validated the process capability study of this particular dimension, which is gear shaft thickness. We have done the CPCPK study, and as per the histogram, we can able to clearly identify that the CPK value have been drastically improved from 0.26 to 1.40 with the very less rejections. And the quality level is achieved, and the consistency achieved to the gear shaft thickness part. Next, as the final step, we have ratified this project with our internal controller, and we could able to save around 0.5 million INR of this project. The quality target is now it is met. And now our third stage of our project, the innovative approach of tool cost optimization using the ML technique, will be explained by my colleague, Mr. Prabhakaran.
Thank you, Mr. John. Let us understand how we reduce our tool cost through innovative method, that is machine learning techniques. When we do the cost breakup of this hydraulic gear pump manufacturing, we are spending more than 10 rupees only for the tools and consumables. On this 10 rupees, major contributor is this grinding wheel, that is a vitrified CBN grinding wheel. And this cost of this wheel is 1.5 lakh rupees. And in a year, we are spending more than 3 million rupees only for this particular tool. The reason behind this high tool cost is predefined dressing interval and manual dressing cycles. We are doing a dressing cycles of 1500 lobe once. Let us understand what is dressing. Dressing is a process of resharpening the grinding wheel over the time. When the grinding wheel became dull, we need to resharpen again. Frequent resharpening means it's a loss to the organization and high cost to the organization. Now we have taken the target to reduce the tool cost by 20%. So we are using a Juncker machine to grind the gear shaft. On that machine, we have the AE sensor, that is acoustic emission sensor, which is emitting vibration signals. When the grinding wheel is sharp, the vibration signals are low. When the grinding wheel is blunt, the vibration signals are more. This contrast, we want to build an ML model, and this ML model will keep on track the grinding wheel and the grinding process. Once the grinding wheel is dull, this ML model will tell the machine to go for a dressing, otherwise no dressing. But the challenges is these machines are very old, and this signal, whatever we are getting, is a 0 to 6 volt analog voltage and need to be converted to digital form. And in the model part, this entire model capturing and deploying on the machine should be in the real-time basis. To overcome this signal, we made an architecture wherein we use the Bosch make IoT gateway, wherein it will capture the signal and convert it to the digital form, and it can also amplify this signal. For the third step, that is the data cleaning and pre-processing is done. And the final step is model building. This model is again deployed to the IoT gateway and to the machine. This is the architecture, and how we build this model will be explained here. The data is captured in a real-time basis in an interval of 250 milliseconds. And in one grinding cycle, we will be getting more than 300 data points. And then these data points are converged using some of the data indicators shown here, or some of them are standard deviation, mean, kurtosis, etc. These data indicators are analyzed using ANOVA technique and ranked them. And when we do the ranking, we found two data indicators are very giving high contrast. One is the vibration peak amplitude. See, when we see here, when the grinding wheel is sharp, the vibration amplitudes are less. When the grinding wheel is blunt, the vibration peak amplitudes are increasing. Similarly, for the standard deviation, when the grinding wheel is blunt, the vibration standard deviation is increasing. These are the two contrasts. Now, these two contrasts are then converged, combined into one single health indicator using a principal component analysis. Here, let us understand how model works. This is the threshold limit, and this blue line indicates this the degradation model. And this our health indicator will keep on adjust the degradation model in a real-time basis. Once the degradation model intersect with this threshold limit, the machine goes for a dressing. Let us understand through a video how the model works. Now the health indicator is adjusting our degradation model. Now this is in a real-time basis. Once the grinding wheel is blunt, this degradation model adjusts quickly this degradation model, and then this will intersect with the threshold limit. Then the machine goes for a dressing, otherwise no dressing. With this entire data capturing and deployed in our Bosch IEP portal, so that the foreman and operator can visualize when the dressing happened, how many parts ground, etc. in a real-time basis. The example shown here is the last dressing is happened from 2159 59th part, that is 30% increase in the tool life. Also the dressing cycle captured by this is the live example of ML model, how the dressing cycle is captured. Coming to the result part, the quality, this particular part, the quality, we have analyzed the surface parameter and metallurgy investigation has come okay. Coming to the cost, we have saved 1.1 million by improving the dressing frequency from 1500 to 2000. Model efficiency is more than 85%. And coming to the standardization, FMEA control plan, everything updated, and the trial order has been approved by the CS, our members. The next step is we have given this project to our Bosch Innovation Team 2021, and we are deploying this particular project to many value streams across our plant. When we see the potential, this particular project is potential up to 50 million INR rupees. This particular idea, adaptive dynamic dressing, is filed for the patent filing. Now coming to the benefits, we are given this benefit in the two stages. One is for Hejjala plant benefit and for the Biddi plant. For Hejjala plant, now the productivity has been increased and plant capacity has been raised to the 4,100 piece. And now the coming to the production comparison from 2020 to 2021, we have increased the productivity by more than 30%. It is visualized here. Coming to the turnover, compared to 2020 and 2021, because of this project, the Hejjala plant turnover has increased to 40%, that is more than 350 million INR rupees. And this is the appreciation mail sent out by the Hejjala plant manager to our team, mentioning the record production for the month of July this year. This slide speaks about the benefits for the Biddi plant for us. By doing this project, there is an additional investment of 52 million for our plant. Also, defect cost has reduced from 0.5 million to 0.1 million. Tool cost reduced by 1 million. Power cost we have reduced. Also, CPCPK increased from 0.6 to 1.4. And by this way, the customer satisfaction has improved from 84% to 95%. Coming to the reward and recognition, as I mentioned earlier, I have given this project in the innovation. This project is selected and awarded as a Bosch Innovation Award 2021, which is highlighted here. This is the highlight of the project. This particular collaboration project is taken as a best example in a Bosch international production network and displayed in our Bosch Germany portal, which is shown here. And this is the again from appreciation mail sent out from our plant manager, Mr. York Byrne, appreciating our project work and the success story. Thank you everybody for listening patiently for our project. Now house is open for question and answers. Thank you.